Okay, let's work on some more predict the product reactions for alkenes and alkynes. The first reaction we have here would be described as an ozonolysis reaction. And remember, that's always going to be a two-step process. So after our workup, we're going to observe the following. The alkene is going to be completely cleaved, so that's the ozonolysis. The lysis part of that means I'm going to break the carbon-carbon double bond. It may help to number our carbons. 1, 2, 3, 4, 5 carbons in the carbon chain in the ring. And so we can open up that ring. It's okay if we keep that in the same orientation we had before. 1, 2, 3, 4, 5. And then what happens is each of the carbons that was originally in the carbon-carbon double bond ends up becoming a carbonyl. So we replace the CC double bond with a CO double bond on carbon 1 and on carbon 5. Both of these are going to, this carbon 1 is going to be a ketone, and carbon 5 is going to be an aldehyde. We could draw on that hydrogen there, and that hydrogen was in the starting material as well. So this reductive workup is what we call it when we have dimethyl sulfide. Is called a reductive workup, and that maintains any hydrogens that were initially on the carbon-carbon double bond stay on the carbonyl. So in this case, we're going to get a ketone, one ketone and one aldehyde product. Okay, the next problem is also an ozonolysis reaction. And here we have both an alkene that will get cleaved and an alkyne that will get cleaved. And this aromatic ring, this benzene ring, is not an alkene. It's an example of an aromatic compound, so there's going to be no reaction at the benzene ring. So that will stay in the final product. So what we're going to have is that benzene ring is still intact, and we're going to break this carbon-carbon double bond and turn it into a carbonyl. And then this carbon up here, this one carbon up here, this is a CH2. And that is still going to be a CH2, but it's going to have a carbonyl attached. So I'm going to get formaldehyde as a molecule up here. And then let's see, we had a, if that's carbon 1, this we could number as 2 and 3 and 4. So this was carbon 2. And then carbon 3, what does that look like? That was a triple bond, and what's going to happen is all 3 of those CC bonds are going to get converted to CO bonds. So what that means is we get a carboxylic acid product out there. So that's carbon 3. And then carbon 4 is just a 1 carbon part. And so that 1 carbon, again, all 3 C bonds will be converted to CO bonds. So I'm going to get a carboxylic acid. I'm going to get 2 carboxylic acids where the alkyne was, and to a ketone and an aldehyde where the alkene was. And notice this is carbon 4. So a good thing to keep in mind when you're doing an ozonolysis is I started out with 4 carbons. I started out with 4 carbons in my starting material in addition to the benzene ring, and I still need 4 carbons, 1, 2, 3, 4 in my product. Now, sometimes you'll see that the when there is a 1 carbon compound, 1 carbon product, as this is called formic acid. Instead, what this is going to continue oxidation in the ozonolysis conditions to give carbon dioxide. So we might see that product drawn either way. Okay, our next reaction looks like we have hydroboration oxidation. So again, a 2-step procedure is described as hydroboration oxidation. And what that's going to do with an alkyne is the same thing it will do to an alkene. It's going to add it's going to break the pi bond and add an H and an OH. So it'll hydrate the pi bond, and it's going to do so in anti-Markovnikov regiochemistry. So anti-Markovnikov regiochemistry, we're going to add an H and OH. So the hydrogen is going to go to the more substituted carbon, and the OH is going to go to the less substituted carbon. And let's just abbreviate this group as a pH for phenyl, so my drawing can be a little a little easier to draw. Okay, so what do I get? What we're going to do is we're just going to break one pi bond, and we're going to add the H and the OH, and that's going to be our intermediate product. Now we stop at this point. We do not add a second equivalent of water, because what we just formed here is a functional group called an enol, because it has the alkene, it has a carbon-carbon double bond, and it's an alcohol, and they share the same carbon. And when we have those structures, those are unstable. This functional group is unstable. It's going to undergo a rearrangement described as a tautomerization. This will tautomerize to give a ketone. Let's see if I can erase that, sorry. It'll tautomerize to give a carbonyl. This case, the carbonyl will be at the end of the carbon chain, so it's actually going to be an aldehyde, not a ketone. So what does a tautomerization mean? We're going to protonate in one position. We're going to protonate here, and we're going to deprotonate up here. So that's all tautomerization is a series of protonations and deprotonations. We have one of each. And so instead of the CC double bond, we're going to get a CO double bond. And so in this case, we're going to get an aldehyde with a terminal alkyne. Hydroboration oxidation gives an aldehyde product. An aldehyde product. We call it that because the carbonyl has a hydrogen attached to it. Okay, what happens if we react an alkyne with HBr in excess of HBr? We are going to break the pi bond and add a hydrogen and a bromine across the pi bond, and then we're going to repeat that process. We're going to do it twice. Now the question here is, where does the hydrogen go? Where does the bromine go? And what we really want to know is, where would a better position be for a carbocation, because that's the mechanism that involves a carbocation. At either position, it would be a secondary carbocation. Okay, but when we put the carbocation here, it's also going to be benzylic, so it would have opportunity to be resonance stabilized. So I'd rather have the carbocation in this position, which means that we're going to protonate in this position to give the carbocation that's benzylic. So wherever the carbocation is, that's where the bromine's going to go. So we're going to do that once, and then we're going to do the same mechanism a second time. So both bromines are going to end up going to the same carbon, and both hydrogens are going to go to the same carbon. And that's going to be our final product. There's no stereochemistry to note in this case because we haven't created any new chiral centers. Okay, how about our next example? We have what's special about this reagent here is I see that we have two oxygens attached to one another. That's described as a peroxide. This is described as a peroxy acid, and this reagent specifically is known as MCPBA. MCPBA, metachloroperoxybenzoic acid. And what that's going to do is that's going to oxidize the alkene and turn it into an epoxide. Now the tricky part here is we want to show that we're going to maintain the stereochemistry. These two methyl groups started out trans to each other. And if I tried to draw it where I just put in the epoxide like this, that would be an improper way to show a chiral center, right? That doesn't make any sense there. So a better way to draw the product would be to put the epoxide ring in the plane. And then how could we show that the two methyl groups are trans to each other? We could draw one as a wedge and one as a dash. That would show the trans stereochemistry. So kind of drawing the alkene on its side, and then bringing in the epoxide, doing the oxidation from the top face here, from the top of the page down, would give me this epoxide. Now, we could also have brought the epoxide from the bottom, or we could decide to swap who's the wedge and who's the dash here. And so what that means is we're going to form both enantiomers. So again, you could just say, plus minus here, that it's racemic, or you could say plus enantiomer, or you could say racemic, whatever you want to say, or you could simply draw the second product. What does the enantiomer look like? The enantiomer would have the methyl on the left as the dash and the methyl on the right as the wedge. That would be the enantiomer. This is a chiral molecule, so we'd always have to form it as a racemic mixture. Okay, and then this last part is reaction is a two-step reaction, two-part reaction, and what we're doing here is we are in the first step using NaNH2, so that means we have Na plus NH2 minus. Okay, so what we have here is NH2 minus. This is a very strong base. And what do bases do? They deprotonate, they react with acidic protons. And the alkyne here has an acidic proton, so we can remove that proton, and that would form the acetylide type anion, where we have a C minus, and that's an okay C minus because it's on an sp hybridized carbon. So this is now a very good nucleophile, and in step 2, the methyl iodide, the alkyl halide, is going to be a great electrophile. So what reaction can happen here is we could get backside attack. We could get SN2, and so we describe this process as an alkylation. An alkylation, we just made a new carbon-carbon bond. A new carbon-carbon bond with a carbon nucleophile and a carbon electrophile. Okay, and this part down below, it continues with predict the product problems, except it now asks you to not only predict the product, but then describe the product in terms of its stereochemistry. So, do we have a single product that has no chiral centers? So, in other words, no carbons with 4 different groups on it that we can name R and S. So that's one possibility. That's an achiral compound. Or is it an achiral compound that is meso? So meso means that you do have chiral centers, but the molecule as a whole is achiral. So both of A and B represent achiral products. Achiral products, just different ways of being achiral. Okay, C is a chiral product that's formed along with its enantiomer, so it's a racemic mixture. D is if we have a mixture of diastereomers, and E is if there's just a single enantiomer. So let's look at each of these examples and see how we would describe the product. So MCPBA, we said that's a way to epoxidize the pi bond. So that happens, both bonds form simultaneously, so we're going to get them adding to the same face. So we could have it as a wedge here. Now this molecule does have chiral centers. This is a chiral center, this is a chiral center. We could name each of these as R or S. But the molecule as a whole is achiral because it has a plane of symmetry. And so when you have chiral centers, but you have a plane of symmetry that reflects one chiral center onto the other, this is the definition of a meso compound. A meso compound. So it is achiral, and it's a single product. Okay, in other words, if I were to draw this with both dashed lines, that would be the same compound just flipped over, like a pancake. So, single meso product. Okay, osmium tetroxide is a way to do a dihydroxylation. So we're going to add 2 OH groups, and we're going to add them in syn fashion. So that means they're both going to be added to the same face. So in other words, we could add them both as wedges or both as dashes. Okay, now when I look at this compound, this is chiral. It's not, it has no symmetry. If I were to rotate around the methyl groups to get them to line up, the OHs would not line up. They'd be a dash and a wedge. So that means we're also going to form the enantiomer. You can't ever form a single chiral product when you start with an achiral starting material. This alkene is planar, it's flat, it's achiral, so it would be impossible to form a single chiral molecule. So you're always going to get a racemic mixture in that case. So what is, how would you describe this? This would be C, a mixture of enantiomers, a 1-to-1 mixture of enantiomers. Okay, in the next case, when we start with the cis alkene, now when we add the OHs in a syn fashion, so that the OH groups end up cis to each other like this. Okay, now we have chiral centers, but we have a plane of symmetry, so it's an achiral molecule. So this is another example of a meso compound. So the answer is B. There's a single meso compound. If I drew these both as dashes, it would be the exact same compound. So there's only a single product. Okay, how about our next example? We have catalytic hydrogenation. This happens with syn addition, but because there's already one hydrogen existing on the alkene, when we add a second hydrogen to that position, it's not going to create a new chiral center, right? So we're going to add a hydrogen and a hydrogen, but we're only going to form one new potentially chiral center. Let's take a look at that. If we draw the hydrogen as a wedge and the methyl as a dash, okay, I'm just going to draw these both flat to emphasize that this is not a chiral center over here. But let's take a closer look at this center. Is this a chiral center? This has two different groups, but then if we look at the other two groups, this is a tie, and we continue down to break the tie. It's still a tie. It's still a tie. So guess what? This is actually an achiral molecule. If I were to draw it like this, it might be a little easier to see. If I were to just draw the methyl exactly lined up with the hydrogen there, you could see for sure that there is a plane of symmetry. So this is not a chiral center. And so which answer best describes this? It looks like it would be a single product with no chiral centers. A single product with no chiral centers. Okay, bromination occurs, it adds two bromines, and it adds them in anti-addition if we want to show one up and one down. Okay, but again, because there's already two hydrogens on this carbon, it can't ever become a chiral center. So there's going to be only one new chiral center here. So let's see what that looks like. So this methyl group was already sticking out. Nothing's happening at that center, so that stays fixed. But the new chiral center we're forming here can be either a wedge, and this bromine we could just draw flat because it's not a chiral center. And let's look at the other product. We can also draw the new bromine bond as a dash. So we've created one new chiral center right here. That's the new chiral center that we formed. So it's going to be formed as both the wedge and the dash. The existing chiral center where this methyl group is has stayed the same. So when we have one chiral center that stays the same and another chiral center that gets inverted, how would you define that? That looks like it is, that looks like it's a definition of a diastereomer. When one chiral center is the same and the other one is different. So that is D, a mixture of diastereomers. Okay, here we have catalytic hydrogenation. We know that that adds two hydrogens from the same face, so syn addition, but because each of these carbons already has at least one hydrogen, it is going to be, no new chiral centers are going to be formed. So our final product is just going to be the alkane here, where now we just have, if you want to draw on all the hydrogens, it's going to be just going to be a CH2 and a CH3. And so what do we have? Just one chiral center. That was the same one that we had existing. So because we started out with a single enantiomer, it's possible to have just a single enantiomer product. So single enantiomer product is E, single enantiomer. I'll write in these labels here because they're off screen. And D, we said these are a mixture, these we describe as a mixture of diastereomers. Okay, and then finally we have hydration. So H3O plus acid and water is a way to add water across a pi bond. This is symmetrical, so it doesn't matter where we add the hydrogen and where we add the OH. Okay, so let's just look at it in that direction. Now the question is, what is the relationship of those two groups that get added? Now because they get added in separate steps, there's no fixed relationship between the two groups. In other words, we're going to get both syn addition and anti-addition. We're going to get both syn addition and anti-addition. So we're going to get the product where the hydrogen adds to the top face and the OH adds to the top face. that would push both methyl groups back. And we can get the hydrogen adding from the top face. Let's keep the hydrogen the same. And the OH adding to the bottom face. So we could get both syn addition and anti-addition. And of course, both of these would be formed with both enantiomers. So again, either whoever we're showing as a wedge can also be the dash, and vice versa. So we get a mixture of stereochemistries here totally. So what is the relationship of these two products? Once again, we could point out that we have two chiral centers. One chiral center has stayed the same. The other chiral center has been inverted. So the definition of that, we would describe these as diastereomers. So we get a mixture of diastereomers here, and that would be D. So just FYI, enantiomers are always formed as a racemic mixture, where diastereomers are very often not formed in equal amounts, because there could be reasons why one of these might be formed faster than the other, depending on what the stability of their transition state is like. So we don't want to, it's not necessary to comment on which of these diastereomers is going to be the major product. There are discussions we can get into about why one might be favored over the other, but just to note that a mixture of diastereomers is typically not formed in equal amounts. Okay, so hopefully this was a nice example. Hopefully this is a nice example of working on some predict the products for oxidations and other reactions of alkenes and alkynes, and then especially taking a look at the stereochemistry and how we could describe these products.